Hello. So today we have Philémon, who's going to talk to us about oriented percolation, or how to never fail coffee again.
Thanks for the introduction. I'm very happy to see many people, and I'm also very happy to do this ZUCMAP presentation. You know, I go there very often to hear about good mathematics and also to enjoy the free apéro. So at some point you have to give back to the hand that feeds you. Maybe a word about me. So I'm a master student here at ETH. Sorry, I study mainly probability theory. Some of you also have me as a TA, and the TA class is today, which means that you will see me for 2 hours. So that's not bravery. I don't know what it is. And today I'm going to talk to you about oriented percolation, which is the subject I came across when doing a semester paper. Of course, it's meant to be a gentle introduction. So even if you haven't seen any probability theory, you should survive this talk. And the first thing I want to say is that, well, arguably, coffee has given a lot to mathematicians. Some would even say that we are somehow machines that turn coffee into theorems. And there is also the less known answer, which is that maybe some of these theorems were better when they were in the form of coffee. So I will not try to argue which theorems should be turned back into coffee, but I will try to convince you that oriented percolation is not such. And so yeah, it's also a time for mathematicians to give kind of to pay back to this coffee which has given us so much, and we'll try to actually study it and see how we can make it better. So the problem we are set with is the following. Let's say you are trying to make coffee, but actually it doesn't work so well. The water that you pour on top of the coffee, it doesn't quite filter through. And then you wonder, maybe I did something wrong, maybe the grinding is too fine, maybe I did not add enough water, and how can I correct my mistakes and actually succeed in making coffee, and how these two parameters will affect the likelihood of you succeeding in making this coffee. And the answer to this problem is within the more general theory of what we call percolation, which is kind of an attempt at describing how fluids are able to penetrate through some porous materials. So some examples could be, well, for instance, you making coffee. But we could also think about maybe, for instance, when you are enjoying some Italian wine. Sorry, it does not seem to be the right picture. Yeah, okay, perfect. So, you know, there's been a bit of a bashing of French wine in the history of ZUCMAP, so I had to re-establish some truths. And these two pictures would correspond to examples of percolation. So you have a liquid which penetrates a material, and we try to see exactly how it manages to go through. Okay, so now that the number of memes has exceeded 200% in the total of ZUCMAP presentations, I have to kind of talk about math. And the first step is to try modeling this idea of liquid penetrating through this material. And the first step will be to give a geometric structure to how the coffee grounds are spread out. And we'll make this assumption that they kind of realize a nice square lattice. All right, and that the water is able to penetrate in between the different coffee grounds. And this will be the lattice that we'll consider in oriented percolation. Actually, it's convenient to rotate it by 180 degrees and to have the orientation up. So what you should imagine is that, well, of course, this is a finite view of an infinite graph, but it's kind of this graph where we pour water, so from the bottom this time because we rotated it, and it kind of tries to make its way up there. And the graph is infinite, but I guess it's kind of for mathematical convenience. Most of the result we deduce will also be, they will be translated into some kind of the finite volume case. So that's for the geometry of the model. And then we have this second kind of assumption where probabilities come in, which is, well, we consider that the water can kind of go through in between the coffee grounds with a certain probability. So if you have maybe some coffee grounds that are wet, then it has more probability of reaching the others, and so on. And that will amount to, well, starting from the graph we had on the previous slide, and well, maybe it starts from being the empty graph, and we add edges, like here with a certain probability, to construct this sort of random graph, which would be a subset of this rotated version of Z2 we were considering. And this formally, well, we put it this way. We consider what we call a configuration, which is just, well, one instance of coffee making, for instance, or one collection of these random edges. So that's just, a set of edges, and we denote the fact that they are here or not, either by 0 or 1. And for every edge that is kind of present in our configuration, then we say that it's open when it's there. When omega of E is equal to 1. And then the probability distribution with respect to which we sample these configurations corresponds to, we start from the empty graph, and for every edge we kind of flip a coin of probability P, and if the coin lands on heads, then we put the edge in there, otherwise we don't put it, and so we give rise to this random graph, right? So each edge is present or not with probability P, and it's all independent. And for those who have followed a bit of probability theory, so if you are wondering about the sigma algebra, we would take this one, which is kind of gives the power sets. So yeah, the boxes in orange will be for those who have seen a bit of probability theory. If you don't understand what this is, it's not really a problem for now. So that's it about how we kind of model this process of coffee making. Also, these, if you think about the problem of coffee, it does not really make sense to have these edges, right, which are not really connected to anything. We really want to think about it as we pour some water from below when it tries to go up. But eventually we'll just, stop looking at them and only look at, for instance, how does the water flow from 0 to, maybe the end of the graph. And the first kind of natural question that pops up is so the problem we had in the introduction, maybe the coffee grinding was too thin, or we don't have enough water, and maybe this parameter that was kind of encoded in P, right, this P that we have here, how does it affect the fact that the water is able to filter through? And the way to put it formal is, we introduced just a bit of notation. So this chi n0 just denotes the set of points I can reach at height n when I start from 0. So in the picture from before, chi of 6, there's a 0 missing, but it would just be these 2 points, right, 0 and 2, which are the only 2 points at height 6 that I can reach from 0. And then the problem of kind of seeing if the water filters through from 0, it amounts to asking if, I have an infinite path that is open, that goes from 0 to plus infinity. And another way you could write it is saying that at every height n, I have some vertices which I can reach from 0. This is the probability that we will look at. It's called the percolation probability, and we'll see that it varies along different values of P, and it has kind of tells us a lot about this random structure. And the first result we are going to see is that this model, it exhibits what we call a phase transition. So there is this threshold for which, there is a critical value of PC, somewhere between 0 and 1, below which this little gadget, theta of P, is always 0, and above which it is strictly positive. Also, for those who know a bit about what's the coupling in probability theory, you can see that this probability is increasing in P, so it's very intuitive. But then to maybe understand it, it's a kind of conceptual twist. So if you don't have seen what a coupling is, I won't insist on that too much. Just remember that it's increasing. And now we come to this idea of phase transition, which is that, so basically this result is saying, so what's important is really that the PC is between 0 and 1 strictly. These two equalities are by definition, right? But it means that pretty much if we plot theta p on a graph, it would look to something like that, right? We have the critical value PC, below which theta p is always 0, so we always fail at making coffee, right? It never is able to filter through from 0. And on the other hand, above PC, so it's the case of where it's the realm of what we call the supercritical regime. Then we have this function theta of p, which is strictly positive and increasing. Well, it's easy to see that theta of p is equal to 1 when p is equal to 1, because I just have the whole graph, and equal to 0 when p equal to 0, but kind of what happens in between is not so clear. And also, so this is just a plot for you to, it's a kind of mental picture, but I haven't told you that theta is continuous, but it's actually increasing, and also you can show that at PC it is equal to 0, which is not, I mean, you can't deduce that from the theorem here. And all that hints toward the fact that we really want supercritical coffee, right? We want a positive probability of actually succeeding. Also for those who have seen a bit more probability theory, well, in the case that we have a positive probability of percolating, then maybe the water doesn't filter through from 0, but almost surely there is another point from the starting axis which will give rise to an infinite path. And now I want to spend just a bit of time explaining the ideas that lie behind this proof, because I think it's accessible to undergraduate level, and I'll try to explain how we can show that this, well, it's proof in 2 steps, right? We show that PC is greater than 0 and smaller than 1. And the first step is actually quite easy. It relies only on, on one little ingredient, which if you have followed probability theory, you will have seen. Otherwise, you can just admit it's the union bound. It's a very easy inequality. So for events AI, I can like sort of take them out, take the union out and transform it into a sum and have this inequality. And now the key observation, which is very simple, is that, well, if we have a path from 0 to infinity, then in particular, we have a path from 0 to distance n for any n that we want. So we can start by bounding this theta of p, the probability of having an infinite open path, by the probability of having an open path that is not infinite, but it just goes to distance n, right? It has length n, and it's open, so omega of e is equal to 1 for every edge, right? And this is where we use the union bound. The idea after this inequality is to say that when n becomes large, then we have more and more path, more and more possible path to go from 0 to distance n, but their probability also decreases because when we add one edge, that's a factor of p that we gain, so we have a total probability of p to the n, and if p is small enough, this counterbalances for the number of paths growing exponentially fast. And this is exactly what we do here. So we use the union bound to sum into all the possible paths of length n. We sum the probability that they are open. This is p. It's exactly p to the n, right? It's a probability that every edge is open and everything is independent. And we get the following bound. And since the number of paths of length n starting from 0 is 2 to the power n every time, right? We choose a direction to go to. Then we get this, which goes to 0 if p is sufficiently small. So we have proven the first part of the theorem, which is that the critical temperature, the critical value PC should be strictly greater than 0, and actually it should be also greater or equal to 1/2, and that's just the argument above that shows it. Is it clear for everyone? If you have any questions, don't hesitate to interrupt me. And the other bound is a bit more tricky. It's using something that we see very often in these kind of random models, which is called the Peyer's argument. So it uses what we call the dual graph, the dual lattice of the one we are considering. And this dual lattice, so maybe if you've had a bit of graph theory, you know what this should be. Otherwise, you can just look at it as just a slightly shifted version of our lattice. So we have edges that pretty much, in blue that was the old lattice, and it defines kind of faces, and on the dual one we have edges between the faces of the primal graph. And then this also comes with a natural, there's a natural way to sample some configuration with a probability. And the way we do it is that, well, in the primal model, so the original model, what I told you is that while kind of the edges going up are present with probability p, and we never look at edges going down. And the natural way to construct a dual configuration starting from a primal configuration is to say, well, for every edge that I don't have, so for instance, this one from here to here is not present in my configuration, well, I have a dual edge, which is just the next one, counterclockwise, which is present in the dual configuration. So I'll have an edge that goes down. On the other hand, for instance, this edge is not present in my initial configuration, so the next one counterclockwise is this this arrow which is present in the dual configuration. And I haven't represented the arrows going on the other way, but kind of from this picture of the arrows going up being here with probability p and the arrows going down with probability 0, then with this counterclockwise maneuver, we get that a dual configuration should be kind of constructed in this way. We have edges with the probability 1 if they go to the right, or 1 minus p if they go to the left. And there's a natural way to couple them, which is how we construct it. So why do we need all that, you might be wondering? And the reason is because, well, when we start from 0 and we explore all the open edges and we try to see if we can go to infinity or not, in the case that we don't manage to, what happens is that there should be some kind of blockade, something that prevents our exploration from 0 to going to infinity. And this is exactly the encoded in this idea of dual graph. So there should be in particular a dual blocking path, so a kind of path going from the right side of the cone to the left side, and preventing our little cluster of 0 to be infinite. And this is exactly what we will use to bound the probability we are looking at. Now the techniques are pretty much the same as in for the first part, the first part of the proof. So I'll just have the picture on one corner of the slide, and okay, that's a lot of equations, but actually it's not so bad. It's pretty much what I said. So if there is no infinite path starting from 0, it must mean that I have some kind of blockade, a dual path, preventing me from being infinite. And then I can again use a kind of union bound. So this time I have more paths because they can start on every point of the right side of the cone. So maybe I denote it by n, kind of so the starting point of my path would be of coordinates n minus 1. And then I have a path which crosses the cone, and I sum over all these. I sum the probability that they are open. And now I need good control on this probability. And what I can say is that, well, coming back from the other picture, going to the left is very costly for the path. It happens only with probability 1 minus p, whereas it's always able to go to the right somehow. So I just need to kind of say how many steps it needs to take to the left to be able to cross this cone, and I should be fine. And it's exactly what we do here. We kind of estimate this number of steps it needs to take to the left. So I'll spare you the calculations, but we end up with something that is strictly smaller than 1 when p is sufficiently close to 1. And we end up with the conclusion that the probability of the complement of this event, which is the probability that there is an infinite path, should be strictly positive, which concludes the proof at this point. Are there any questions? Okay, so that was kind of the first results about this probability of the coffee making it through our model. And now we want to look about something slightly different. I wanted to mention that. So the critical temperature, like when we are at PC, then the probability to have this infinite path is 0. And for other types of model, it has been established that it decays with this very surprising polynomial. So for oriented percolation, we don't have such a precise description of the probability, but we kind of know it's squeezed between two polynomials. So there's something a bit wild going on at PC. Okay, and right. So now I want to talk about something else we can see that depends strongly on the value p that we have within our model, which is what we call the angle. For that, we need just a bit more notation, and we'll denote this Rn, which should be the rightmost vertex of height n accessible from 0. So before we had, this object chi n 0, which told us which vertices we can access from 0, and this Rn is just the supremum of them. The problem with this is that, maybe this is not really well defined for every n, because if I don't have an infinite path starting from 0, then at some point I do not have any points that I can access from 0, so this supremum is going to be minus infinity. So we want just to generalize a bit further and define these Rn bars, which should be the rightmost vertex of height n accessible from the left side of the interval we start with. So from minus infinity 0, and also you can define the leftmost accessible vertex symmetrically, and you can check that these are well defined almost surely. They are even integrable. So they are finite, whereas ln and Rn might not be. So maybe I'll show you a picture. It's worth 1,000 words, right? So in this case, we have very few edges, and from 0 we are able to go to height 1. So we have this R1, which would be equal to 1 in this case. But since it's not connected to a height 2, then my R2 will be minus infinity, because there is even no vertex I can look at. On the other hand, maybe I go further to the left and I meet a point at which I can go to height 2, and the first time at which I can do this gives me this R2 bar, and then maybe I have R2 3 bar. I have to go even more to the left, and so on. And so these are two different objects, but in the end they are quite related, because when we look at the events omega, which is the event that I have an infinite path, so I start from 0, I can go to plus infinity, then it's quite easy to see that actually they should be the same, right? These Rn and Rn bar, and also we have this inequality that the leftmost accessible vertex should be smaller than the rightmost accessible vertex, so without the bars, which is pretty intuitive. But if we add the bars, then maybe this might not be the case. And then maybe from this picture, if you kind of see one step ahead, you would be thinking, but I have some kind of stochastic process that evolves with n. It has jumps and so on. And since everything is independent, maybe I have some kind of random walk structure. And unfortunately, you would be wrong. But you will not be so wrong, because, if we introduce yet another process, which I promise is going to be the last one. So this one is a bit harder to make sense of, but the way that you see it is, if you are at R1 bar, you can say that pretty much you forget about what has happened below, and you restart the whole model from this height 1. And then you look at, so R bar 1, 2 would be exactly R1 bar in this new model. So you go to the left and you go up once, and you meet this R1, 2, which is equal to minus 1. It's pretty much translating this R1 bar to being the origin of a new model. And similarly, you have this R bar 2, 3, which is minus 3 in this case. And now we are happy because we have some kind of not really sub-additivity going on, right? The fact that we restart tells us that these three quantities should be related, and we have some form of sub-additivity on the model. And this is very interesting, because if we had some form of random walk, then we will be able to deduce, so for those who follow probability theory, that if I have a random walk Sn and I divide it by n, it should go to the expectation of every step I take. That's the law of large numbers. And here we don't have exactly additivity, but we have sub-additivity, and there are some results we can use in this case. And some results already are present in the deterministic case, and that is the form of what we call Fichte's lemma, that maybe you have seen in, I think, personally I had seen it in an exercise in analysis one. So it's a standard result about sub-additive sequences, which tells you that actually an over n always converges when you have a sub-additive sequence. And you can even say what the limit will be, and it will be the infimum of these values of an over n. So, okay, don't take n equals 0 here, but you got the idea. And in our kind of random setting, we also have a result of this type, which is harder to establish because of every random phenomenon that goes on. But what we can say is the following. It's the content of the Liget's ergodic theorem, which tells you that this Rn over n also converges to something which is reminiscent of this infimum, and actually it's the infimum of this average of Rn bar over n. For those who know what this means, the limit holds almost surely n in L1 when the right-hand side is finite. So, of course, it's going to be smaller than 1, because remember that Rn bar can only go to the right with an angle of 45 degrees. So Rn bar over n is smaller than 1, but it, in theory, could be equal to minus infinity. And that reminds me that I wanted to show you some simulations, and I forgot to do it, so I'll do it now. So this little Python script, so it's really badly written, but it samples some configurations. So here I have a probability p, which is very close to the critical probability, and I sample over like a height of 100, and we can see what a typical cluster would look like. So that would be something like this. I only represented the ones that I can access from 0. So of course, the rest of the picture would be filled with other edges. So in this case, I was lucky. I managed to reach height 100, but maybe if I try again, I don't quite reach it. So it's slightly translated, but I only reach a height 70, and then I die out. And if I run it again, this time I survive barely, and this time I died out pretty quickly. So it's just over here, my little cluster. So this is kind of to show you that, sometimes we're lucky and the coffee process works well, and otherwise it does not. All right, I will show you some other simulations later on, because this Rn bar over n and this alpha, this angle, are pretty interesting, and you can already see them on the simulations. And okay, this is my next slide, actually. So here I simulated up to, I think, 1,000 or something. So you have a better picture of what it should look like on large values of n. And on the critical case, well, you see that the cluster is super thin, right? And this is due to the fact that, as we will see later, the angle at the critical value PC should be equal to 0. So if you see this cluster, which it's bound to die out at some point, but maybe I'm lucky and I observe it surviving up to very high values of n, then it should in any case be super thin. And if I increase slightly the value of p, then already at p equals 1.66, I see this kind of cone, right? All the vertices I can see from 0 should describe a cone, and the angle of the cone is exactly this value alpha that I introduced before. And if I go to 0.68, then this is even more. You can see it even more. This idea of angle, and it should go to alpha equals 1 when the temperature is when p is equal to 1. Okay, and actually these two things that we've seen so far. So on the one hand, the probability of percolating, the probability of having an infinite path from 0. And the angles are two things that should be closely related. Here is a proposition with some different links we can explore between the two. So I will not prove this, but just give you kind of the idea. So the first thing is that if the angle is negative, then the probability of having an infinite path should be 0. And this is not too surprising because, so you should look at this first item. So if the angle is negative, it means that these two processes, Rn bar and Ln bar, will kind of depart from each other at some point. And it's impossible to have an infinite path, because if I had such an infinite path, starting from 0, then this Rn bar should be really equal to Rn, or Ln bar equal to Ln, and the leftmost accessible vertex should be to the left of the rightmost accessible vertex. So I can't really have this situation where they stop seeing each other after a while. On the other hand, if the angle is positive, then I also have a strict probability of having an infinite path. And this is a bit harder to conceive, but the idea is that if my Rn bar, so if the angle is strictly positive, then Rn bar, it should look like something of the form alpha n. And if alpha is positive, then it goes to plus infinity. On the other hand, ln bar goes to minus infinity. And somehow, if we manage to reach this kind of intersection point from 0, then we will be inside a cone that we know will never die out, because Rn bar goes to plus infinity, ln bar to minus infinity. And of course, you have to formalize this, because this kind of intersection here is random, so you have to be a bit careful. But that's how I understand the underlying idea of this item of the proposition. If the angle is positive, then you have a positive chance of reaching this intersection point, and then you know you'll be going to infinity. And the third item is that, to answer the question at PC, it's much easier for the angle than from theta p. Proving that theta p c is equal to 0 is hard. Proving that alpha pc is equal to 0 is all right, I would say. And at PC it's equal to 0, and when p is smaller than PC, it's not equal to 0, but to minus infinity. So Rn bar, it goes to minus infinity very, very fast. So we can refine our older picture and have something that looks like this. So I added a little plot for alpha of p. Below PC, it should be equal to minus infinity. Above, it should be positive. At 0, it's equal to 0, and there are some more results I did not talk about, but you can pretty much also compare alpha p and theta p. You can show that alpha should be somehow above a linear function of theta of p and so on. So it's kind of the picture that you get at the end. Also, you can show that alpha of p is differentiable and so on. But I don't have time to talk about all that. What I want to do now is just mention what happens if we are not if we are in the subcritical regime. We know that we have 0 chance of going to infinity, but actually there is a result that tells you that even reaching distance n is quite hard, and it's exponentially hard in n. That is a result. For that, we need subjective concentration results. So this is easier to understand if you've seen a bit of probability theory, but it pretty much tells you that Rn bar over n should be very, very close to alpha. It cannot be close to beta for beta greater than alpha, otherwise this probability decays exponentially fast. It cannot either be far from alpha below, otherwise we have the same kind of behavior. So Rn bar over n should be very, very close to alpha. And actually, there is a result that says that this Rn bar over n converges to a normal random variable, which might be surprising for some people, might not be for others. You know, in probability, usually in 99% of the cases, when you have something that converges, it converges to a normal random variable. And if it does not, it's because it converges to 0, but which is a degenerate random variable. So all is well. And from these results, so if you just admit these concentration results, then we have the following, what we call the sharpness. So if we are below the critical temperature, then already reaching distance n is exponentially hard, as I said. And this is not too hard to prove. Maybe I don't have time to explain it, but pretty much you compare the probability of not going to distance n with the probability of having the angle in the two processes in the wrong way. And because the angle, in our case, we are below PC is minus infinity, then by using the result from the last slide, you see that this is exponentially low. So coming back to our coffee problem, if we are in a subcritical case, we are kind of doomed because it's very, very unlikely that we will succeed in making coffee. Whereas on the supercritical case, we have kind of a relative of this result, which tells you that, well, if you reach distance n, then you have very, very good chances of going to plus infinity. Or to say it differently, if you reach distance n, the probability that you don't reach plus infinity is exponentially small. Okay. There is one last aspect of this oriented percolation I would like to mention, which is the fact that you can look at probabilities of some rectangles of being crossed. So just to say a few words about this result, it tells you that if you have some boxes with dimensions 2m, m, and 2n, the probability that you observe an open path that crosses the box vertically in the one case, so from the bottom to the top, or horizontally from the, say, left side to the right side, if this is small in the first place, then when we scale the dimensions of the box, it becomes exponentially smaller. So, so this is super exponential, but if I scale by n instead of 2k, then I have exponential of minus c times n. So this again kind of describes the geometry of what's going on, and well, it's easy to kind of see conceptually that if you are in this case, then you should be in the subcritical regime, because, I mean, if these crossings are already unlikely, how unlikely is it going to be to reach plus infinity, right? And there is also a kind of converse which tells you that if you are subcritical, then you can find such unlikely crossings. And this is kind of cool because you can deduce this sharpness ID again from it by saying that to be connected to height 2kn, then you must either cross the blue box from bottom to top, or one of the two red boxes, which go all the way down here, from right to left or from left to right, and then you bound again by the previous result, and you get this kind of exponential decay. And yeah, in general, you have this sharpness result. And all right, that kind of concludes what I wanted to say. So this model of oriented percolation, it has these different perspectives where, on the one hand, the fact that we have this orientation allows us to study a stochastic process that evolves on the right most accessible vertex, on the left most accessible vertex, and we can deduce some results in this favor by using standard, either concentration tools or things that would be similar to random walks. And we also have these perspective of crossings, which come more from the realm of non-oriented percolation, which I don't have time to talk about now, but these kind of two pictures, they talk to each other, and they are able to provide somehow different proofs of the same results. So yeah, I mean, I tried to explain how you can make coffee. I haven't really told you if I can make good coffee, but that would not really I'm not really able to answer that as a mathematician, so I'll just leave you with that, and thank you very much. It's certainly trickier. Independence is something we really like in probability theory because it allows to do all these, to transform all these probabilities. But it's also, non-dependent percolation is also very well studied by some people. There are kind of some weaker consequences of independence that you can transfer to this dependent model, like some sorts of inequalities that maybe you cannot write the probability of an intersection as the product of the probabilities, but there are some inequalities that you're able to use and to deduce similar type of results. And I think particularly this second theory with the crossings is something that you can study also in the case of dependent percolation. Also, this process Rn and Rn bar, so if you don't have independent edges, but maybe, when you start from one edge and you have one which is of a factor n above, you can expect that they would be independent, okay? So maybe two neighbor edges will not be independent, but if they are at two distance away, they would be, or something. So you would have what we call a two-dependent model. And instead of looking at Rn bar, you could look at R2n bar, and you would still have some kind of independence going on, and you would be able to deduce similar type of results. So I'm not sure I understand exactly, but you know that they will meet, because when the angle is positive, Rn bar is like alpha of n, Ln bar is like minus alpha of n, so since you have almost sure convergence, you can translate that into convergence in probability, for instance, and you'll see that.
It's not important where
For this argument, not really. It's just that the fact that this meeting point is random makes it that you have to be a bit careful when writing down the argument that you just want to reach this intersection point. But if you use convergence in a probability argument, you say that with high probability, this intersection point should not happen above a certain height, and then you say, but the probability that reached this height in the first place is very high. I mean, it's strictly positive. So you combine the two and you deduce the result. Okay. Other questions? Well, in this case, thanks again for your attention. Thanks to people organizing ZookMap, and see you in the apéro.
Hello? Yeah, okay. Thank you for coming. This week, the common room is being used by the ETH, so we will have the apéro in CAB G56. See you there.